Hello guys, welcome to the Deep Diver screencast. We are all graduate students in Brown Data Science Initiative. I'm Hada Song. In this video, I'm responsible for the introduce overview and data preprocessing and baseline models.
Hello everyone, this is Yu Yang Li. I'm gonna walk through our ResNet model and the EfficientNet model.
Hi everyone, I'm Suyuan. I will be in charge of the introduction of our self-design model and the reflection.
You guys can find our blog post using the link here. And here's the Kaggle page. So this project is the public cassava leaf disease classification computation on Kaggle. Our goal is to classify each cassava leaf image into 4 disease categoricals or a 5th category that represent a healthy leaf which would potentially be beneficial to local farmers. So this is our first blog post. In this stage, we mainly focused on data exploratory and baseline model. In this class distribution plot, we can see class 3, cassava mosaic disease, has a much larger proportion than other 4 classes. This reveals our data is imbalanced, so we may need to consider the stratified data splitting method. In this method, the folds are made by preserving the percentage of samples for each class. We used 96 times 96 resized images with a stratified method at this stage. I will discuss the conflict between the stratified method and storage memory (RAM) due to resizing. We could see the characteristic of each class clearly, like yellow and withered shape of leaves in class row. More details about the characteristic and background of illness could be checked out on this blog. And here is our second blog. So in this stage, we introduced 3 new models: ResNet, EfficientNet, and self-designed model inspired by combination of VGG and ResNet. So for our EfficientNet, EfficientNet is a very deep convolutional neural network architecture that was proposed in 2019. But we can see from this plot, it reached a very good accuracy score with a faster speed compared to other models like ResNet 50. Also, we selected ResNet since it does not need to fire all neurons in every epoch, which means after one data feature is learned, it will not try to learn it again, but pay more attention on learning new features. We will also spend our time on tuning hyperparameters like learning rate and number of epochs. So in our final blog here, as I said previously, we know the truth that class 3 has the much larger proportion than other classes, so the data is imbalanced, and our prediction would be biased if we only split the original data randomly. However, we cannot balance the trade-offs between image resizing and handling imbalanced image due to the limitation of RAM and the stratified method. For example, we could at most resize the image as 128 times 128 with stratified data splitting, but the larger data size of the image are, the more information preserved and the more accuracy would be reached by the algorithms. So for the optimization purpose, we use the TF record format since we would like to have a 256 times 256 pixels or above resized image, but the data TF record given by the Kaggle is not stratified. Fortunately, thanks to the Kaggle Dimetro Olivier given by the 15 stratified TF record file in her public Kaggle page. So we decided to use these TF data files. Each file contains 1427 examples, and it keeps the same percentage of each class as it is in the original data. For our baseline model, this is our final baseline model. So comparing to the original baseline model, so in the TF records, the original data, original baseline model provides us constant accuracy and losses, which means this model didn't learn from the start. Therefore, we firstly changed the max pooling to average pooling in the first two convolutional blocks to keep the information as much as possible and use the max pooling to catch the characteristics of the information in the last block. After three convolutional blocks, 5 classes are classified in the last layer. Dropout method in the model and early stopping prevent the overfitting issue. Compared to the baseline accuracy 0.615, which calculated based on the class with the largest proportion class 3. Before overfitting, the baseline CNN model gives us 0.67 accuracy, which improves 0.055 accuracy. So next, I will let Yuyang Li introduce the ResNet and the EfficientNet.
So I'm gonna walk through our ResNet model and EfficientNet model. So over here, as you can see, this is our ResNet model structure. In the finalized version of our ResNet model, we basically continue with the last structure. We try different batch size values, and it gives a pretty good outcome. So as you can see, this is our final prediction results graph. The ResNet model has a steady performance as both training and validation accuracy are increasing during epochs, and the losses are decreasing before epoch 5. The model has a slight tendency of overfitting, so we use early stopping and reduce learning parameters inside this model. Overall, the model performance has a comparative prediction accuracy as the CNN model, in which it gives an accuracy score of 0.67 for epoch 5. And the next model I will present is our EfficientNet B0 model. As you can see, this is an illustration of EfficientNet B0 model architecture structure. So for our EfficientNet B0 model, we use the structure of B0 instead of B4 structure, as we did it during the midway, because the increase of the model depth by introducing a B4 structure doesn't have any significant effect on prediction accuracy. We also initialize the weights of the model's head layer to ImageNet. And the plot here shows the loss accuracy result of our EfficientNet B0 model. As this model gives the best performance among all our models we tried so far. The training and validation accuracy curves both increase during epochs. The curve of training and validation losses are gradually decreasing with minor fluctuations. In the end, we reached the best validation accuracy score of 0.82 for epoch 11. Next, I will let Siyuan Li to introduce our self-designed model.
Okay, thanks, Yuyang. In the next part of introduction, we'll be focused on our own self-designed model structure. So At the beginning of experiment step, we combine the convolutional layers with VGGNet to set up the structure. We achieve a satisfying result during the midway process. However, for the final version, we introduce more powerful nets to help us facilitate the prediction accuracy. We increase the depth of the model. The ultimate model combined the CNN baseline model, VGGNet, and ResNet together to build up the structure. Here is a summary of our model. You can go through the layers with me together. And next, I would like to show a picture of this model performance. We can see that both training and validation accuracy line are increasing during training epochs. Meanwhile, the loss curves of both training and validation are decreasing gradually. The best validation accuracy is achieved at epoch 4, which is about 0.688. Although the model is not the best comparing to other, it is still show a great improvement, about 11.8% growth from the baseline accuracy. So this is the introduction for our self-designed model. Our finalized model selection is the efficient net with B0 structure. The best validation accuracy we have is about 0.8. Well, at last, let's move to the part of reflection. In summary, we experimented 4 different network models for the leaf disease prediction. Reflecting on the previous research, we could make more improvements in future. First thing is that in the data processing process, the stratified 256 times 256 time record data was used in current prediction. However, due to the limitation of RAM, we hope to have higher resolution of resized image or TF records data to increase the prediction accuracy in later experiment. The second point is that we saw our models have a tendency of overfitting issue at the early stage of training epochs. So we are considering to apply regularization techniques such as adding latch or lasso terms into the model to help ameliorate the situation. At last, there are a lot of networks we didn't try. We hope to continue the experiment of those state-of-art techniques to help us for the prediction, and we might obtain some surprising results in the future. We are hopeful of this process. Thank you all.